Wormholes, are they real and how do they work? The concept of wormholes has fascinated humans for centuries, presenting the possibility of traveling vast distances across the universe in the blink of an eye. But are wormholes real, or are they merely a product of science fiction? In this article, we will explore the fascinating world of wormholes, their theoretical basis, and the potential for their existence. Einstein's theory of relativity, proposed in the early 20th century, introduced a profound shift in our understanding of space, time, and the nature of the universe. Prior to this groundbreaking theory, space was commonly regarded as an immutable and fixed stage upon which the celestial dramas unfolded. However, Einstein's revolutionary insights unveiled a more intricate and dynamic reality. According to the theory of relativity, space and time are not separate entities, but are intricately intertwined to form a unified fabric known as space-time. This fabric is not rigid, but rather flexible, capable of being influenced and molded by the presence of matter and energy. In other words, the presence of mass and energy can cause space-time to curve, creating what we perceive as gravity. One of the remarkable consequences of this theory is the concept of gravitational waves. Just as a stone thrown into a pond creates ripples that propagate outward, the movement of massive objects in space can generate waves in the fabric of space-time itself. These gravitational waves travel through the universe, carrying information about cataclysmic events, such as the collision of black holes or the birth of stars. Thus, Einstein's theory has been experimentally confirmed on numerous occasions, solidifying its status as a cornerstone of modern physics. Its profound implications continue to shape our understanding of the cosmos, from the behavior of massive celestial bodies to the evolution of the universe as a whole. The concept of Einstein-Rosen bridges, also known as wormholes, was indeed one of the earliest theoretical descriptions of connecting different regions of space-time. While the concept of wormholes has been explored in science fiction and popular culture, it is important to note that their existence and properties are still purely speculative and not supported by current scientific evidence. According to the Einstein-Rosen bridge idea, a black hole could potentially serve as a portal or connection to another region of space-time, possibly a parallel universe. In the visualization you mentioned, empty space-time is depicted as a flat sheet that becomes curved around massive objects, such as black holes. When the curvature becomes extremely intense, it can lead to the formation of a black hole, accompanied by the creation of an event horizon, a one-way barrier beyond which nothing can escape, including light. Inside a black hole, the singularity is typically described as a point of infinite density, where our current understanding of physics breaks down. However, it's important to note that our knowledge of physics at such extreme conditions is incomplete, and a theory of quantum gravity is needed to fully understand what happens at the singularity. Regarding the possibility of a parallel universe beyond the event horizon, where time runs backward and resembles a white hole, this is a speculative concept. While white holes are theoretical solutions to Einstein's field equations in general relativity, they are not yet confirmed to exist in nature. White holes, if they exist, would be like the reverse of black holes, expelling matter and energy rather than absorbing them. However, the idea of white holes being connected to black holes through wormholes is purely theoretical and not well understood. Traversing wormholes, even if they were to exist, poses significant challenges. One of the major issues is the requirement of exotic matter with negative energy density to stabilize and maintain the wormhole. The existence of such matter is purely hypothetical and has not been observed in nature. Additionally, the enormous amounts of energy and the infinite amount of time required to travel through a wormhole make it currently beyond our technological capabilities. It's important to distinguish between the scientific speculation and the popular portrayals of wormholes and parallel universes. While these concepts can be fascinating and inspire imagination, they remain speculative and subject to ongoing scientific investigation and theoretical development. For practical interstellar travel, a different type of wormhole is needed, the traversable wormhole. If string theory or its variations accurately describe our universe, it is conceivable that countless traversable wormholes already exist within its fabric. These wormholes may have been created during the rapid expansion of the universe after the Big Bang through quantum fluctuations at the smallest scales. At the smallest scales, threaded through these wormholes are cosmic strings, which are remnants from the early universe. These cosmic strings could connect distant parts of space-time, potentially allowing for faster-than-light travel. Some physicists even speculate that supermassive black holes at the centers of galaxies could be wormholes, offering tantalizing possibilities for exploration. While wormholes present exciting opportunities for space travel, numerous challenges must be addressed. For a wormhole to be traversable and useful, it must possess specific properties. Connection. A wormhole should connect distant parts of space-time, enabling travel between 2 points separated by vast distances. Two-way travel. It should allow for travel in both directions, without the presence of event horizons that would restrict movement. Size and safety. The wormhole must be of sufficient size to avoid gravitational forces that could be fatal to travelers. However, the most significant obstacle is the propensity of wormholes to collapse due to gravitational forces. Gravity constantly attempts to pinch the wormhole shut, transforming it into a black hole. To counteract this effect, an exotic form of matter known as exotic matter with negative mass is required. This exotic matter would exert repulsive forces, effectively keeping the wormhole open against the pull of gravity. The vacuum of space itself, with its quantum fluctuations, may hold the key to creating the necessary exotic matter. By manipulating these fluctuations, scientists could potentially stabilize the wormholes and keep them open for travel. While the theoretical underpinnings of wormholes are captivating, they also raise profound questions about the nature of the universe. Some scientists argue that the existence of traversable wormholes violates the fundamental principles of causality and creates the potential for time travel paradoxes. As a result, they believe that wormholes may not be feasible or even possible within the laws of our universe. Nevertheless, the exploration of wormholes remains an active area of research, both theoretically and experimentally. Scientists continue to investigate the potential existence of wormholes, seeking observational evidence or indirect indicators that could support their existence. Advanced technologies, such as gravitational wave detectors and high-energy particle accelerators, may provide insights into the nature of space-time and shed light on the existence of wormholes. In the realm of practical applications, the concept of man-made wormholes opens up exciting possibilities for interstellar travel and the colonization of distant worlds. By stabilizing wormholes with exotic matter, it could be conceivable to establish a network of interconnected wormholes, allowing for rapid travel between different regions of space. This could revolutionize human exploration and potentially lead to the emergence of interstellar civilizations. However, the challenges and ethical implications associated with wormhole travel cannot be ignored. The disruption of causality and the potential for altering the course of history raise profound philosophical and ethical questions. Before embarking on the journey of creating and utilizing wormholes, thorough scientific, ethical, and societal considerations must be undertaken. In conclusion, While wormholes remain a captivating concept in theoretical physics, their existence and practicality are still subjects of intense scientific investigation. The quest to understand the nature of space-time, unravel the mysteries of the universe, and unlock the potential of wormhole travel continues to inspire scientists and thinkers alike. As our understanding of the cosmos advances, who knows what incredible discoveries await us in the realm of wormholes and beyond.